One application of linear equations that we use a lot is linear interpolation. So we're going to look at what interpolation means and how we can apply it in engineering concepts. While we're talking about interpolation, we can also talk about extrapolation. While interpolation has some concerns, it's a lot more concerning to use extrapolation, and we'll explain that in this video. To define the difference between these two, we can look at a graph. Interpolation and extrapolation typically is used when you have a table of data sets or you've run some experiments and you want to know the expected values at points you didn't run the experiment for. So let's say here we have 4 data points. Now the x-axis can be anything. It could be at a certain temperature, you measure the strength, and that's what you measure in the y-axis. Or you run something for a given amount of time and your x-axis becomes your time axis. And so you measure the distance something travels over amount of time. So then your y-axis would then be a distance value. So these x and y axes are pretty arbitrary. The main point is you have at some x values the performance or the measured value, which is your y value, right? And you want to find data points at some different x value. So when we say we want to extrapolate that data, that means that we're looking at beyond the range. So within these 4 data points, within the range will be the x values between something like what, like 12 to 2. And something out here would be extrapolation because you're extrapolating beyond. Now the concern there is the physics or whatever's defining the relationship in this range may or may not be true out here. So that's something that you either need to make an assumption of, or you need to know something about what's going on physically before you can define the extrapolation and make sense of that data point. Interpolation is if you're looking at within the range. So let's say within the range of these 2 points you're interested, then you can do, and this would be considered interpolation. So it's between or within the range of data points that you have. So let's walk through the idea of linear interpolation. We're going to use a graph to help us visualize it, and then we'll do some examples without looking at graphs whatsoever. So let's say I have collected data at some x equals 2 and x equals 10. All right, so there are my 2 data points. And I'm interested in using linear interpolation to define what the y value is at some x equals 6. Okay? So when we say linear interpolation, because there's many types of interpolations, we're looking in this section only at the linear type. We're saying that the 2 data points that we're using to do the linear interpolation for the 3rd unknown data point is linear, or we're using a straight line, right? And we've been using equations y equals mx plus b, looking at this straight line through this series already. So just looking graphically here, we can see this line intersects the x equals 6 vertical line at some y equals 5. Right? So graphically, that's easy. You have 2 data points, draw a straight line. Where along this line does some x value cross? We've done this. You can think about this from a intersection of lines perspective. You can think about it as solve for y equals mx plus b for these 2 data points and plug in an x value. So it's quite straightforward. But let's do this without using the graph. And there's really 2 ways people have looked at it. I tend to look at it, think about it from one perspective because you don't have to memorize anything. But others like the final form, so you just plug it in. So I'll leave it up to you which method. I'm going to show you one specific method here. Okay, so let's take a look at this example, and we're not going to just use the graphical way to help us interpret this. So again, we have two data points given to us, 2, 1 and 10, 9. Okay, and we're trying to identify what is y at x equals 6. So what we're going to try to use is the fact that we have a straight line. All 3 points lie on this straight line. You could also think about this as these 2 points, the first 2 given points, x equals 2 and x equals 10 points, are the same, fall along the same line as x equals 2 and x equals 6, or x equals 6 and x equals 10 points, right? You can break this up into 3 separate lines and say they all fall along the same straight line. So one way I like thinking about this is that all of these 3 lines have the same slope, right? If they're the same line, then they have the same slope. You know, they also have the same y-intercepts, but think about them from a slope perspective is easier, as you'll see in a second. Slope is defined as rise over run, so y2 minus y1 over x2 minus x1. And I'm thinking about x like 0.1 as this given one, 0.2 as this second given point, and you can think of x3 and y3 as your unknown y term. So if I write out the slopes of these 3 broken out lines, I can say y2 minus y1, x2 minus x1, that's these terms right here, right? There's y2, 9, there's y1, 1, and then x2 minus x1, there's my x2, 10, and my x1, 2. Then we do the same thing, but now we use the unknown point. So I put that in red here. So y minus 1, and you have to be consistent. The main thing you have to be consistent. You put your y values in the numerator, your x values in the denominator, and you have to be consistent in each ratio, right? So this would be 6, the unknown, minus 2. Or I can use 0.2 and 0.3. So 9 minus the unknown y, then 10 minus 6. So as long as you're consistent, it doesn't matter if you put y's in numerator or denominator, because you're just picking the set of two ratios to compare, right? So I don't need all 3 of these. I could just look at these 2, or I can look at this this ratio and this ratio. It's really up to you which one. But one of your ratios has to be the 2 points that you are given, right? So you can solve for this easily, right? That the slope is equal to 1, and so you can either use this and solve it for 1, or this and solve it for 1, and we could see easily that y is equal to 5, right? 5 minus 1 equals 4, so that makes this ratio 1, or 9 minus 5 is equal to 4, and that also makes this ratio equal to 1, right? So we're consistent. So we can see how we can use just equating the slopes to get our unknown y value, and that is all linear interpolation really is. Now, if you search online or if you look through your textbook, you might see an equation that looks similar to this. All this is looking at these ratios and isolating your unknown y value. Because if you take the ratio y2 minus y1 over x2 minus x1 and equate that to a y3 minus y1 and divide that by x3 minus x1, you get this same equation. So I suggest thinking about it from a slope equality perspective. That way, on an exam, you just need to memorize that the slopes need to be equal, and it takes 1 or 2 steps longer. But that way, you won't accidentally swap values or swap signs, which is a common thing to do if you just try to memorize this equation. Now, this equation can be useful if you program this equation into your calculator or on Excel if you need to do a lot of linear interpolation. That's perfectly fine. But I think doing a couple linear interpolations by hand, so make sure you understand the concept and what to look for is useful. And then afterwards, in my opinion, if linear interpolation is not the focus, because a lot of times for engineering classes, we're using linear interpolation just to get a data point and then using it to solve a bigger engineering problem, then I don't want linear interpolation to be the focus. Then you can use the program and you can use this equation. But when you're first learning it, I definitely suggest thinking about it from a common slope or a equal slope relationship. So now we're going to look at a couple examples where we actually apply this. In a thermodynamics class, you'll see a table similar to this, right? Here we're given properties of a saturated water, right? So at given temperatures, here we're shown at 5 degrees Celsius increments, we're given the saturated pressure, the specific volume, which is basically 1 over density, that's why it's in cubic meters per kilogram, and internal energy, that's why it's in kilojoules per kilogram, right? So the energy per mass of water. We're told because it's saturated water, it's in that transition phase. So there can be fully liquid, it could be fully vapor or something in between. So that's why we're given saturated liquid, saturated vapor, properties of both specific volume and internal energy. So the way we're going to look at this, and if you don't understand exactly what saturated pressure, specific volume, or internal energy mean, that doesn't matter for this video. We're not looking at the properties and applying it to an engineering problem. We're looking at how to pool these properties. That's the main thing here, right? So what these actually represent for the purposes of linear interpolation are not crucial, okay? But how they're used and how we pull from a table here is going to be the same way that you pull from any type of table. So that's why this is a good example. So we're asked to identify the specific volume, right? That's this symbol here. Subscript G represents that for a saturated vapor. So we're looking at this column here at some temperature 6 degrees. So if I asked you at 5 degrees, it would be as simple as pulling this value here. Then it would be 147.03 cubic meters per kilogram. But linear interpolation in general is the purpose of it is to utilize a table where you don't have a value directly on the table. So the first step is to find your x-axis and the data points that you're going to use. In this case, the x-axis is going to be my temperature because that's what I'm given here. So the first step is what range, or in this case, what rows will I use to identify the specific volumes that will apply in my linear interpolation. So 6 degrees, because these are 5 degree increments, is going to be best between 5 and 10 degrees Celsius. And then my specific volume column right here for saturated vapor. So these are the values I will be using, 147.03 and 106.32. I'll also be using the temperatures, 5 degrees Celsius and 10 degrees Celsius. So now I'll apply the equivalent slope equation, right? So just remember, the y values, the rise values, are going to be my saturated vapor specific volumes. The run values, or my x values, are going to be my temperature values. And so we set up the slopes. So I'll walk through this one a little slowly, and then the future examples I can go through quickly because they're going to be the same thing repeating, right? So I like to put in my numerator the rise terms, but if you don't want to and you want to put in the denominator, that's okay, as long as you're consistent. So I put what I'm searching for as my top left value, right? So the specific volume, I put subscript G at 6 degrees Celsius to remind myself which value what temperature and what property that's at. All right, so saturated vapor at 6 degrees is what I'm looking for. So I subtract that by another specific volume, right? I like to keep the units here so that I don't mix terms up. If you just put numbers, it's really easy to mix terms up. So cubic meters per kilogram, I want this to be the specific volume of saturated vapor at 5 degrees, so 147.03. And I divide that by the run, or the x values. So I take, right, you gotta be consistent. So this temperature has to be matched with this specific volume, so 6 degrees, minus the temperature that matches this specific volume, which is 5 degrees. So I just look at this row, and I relate it to my unknown. And I equate that to the slope of the known values, or those are the values at 5 degrees and 10 degrees. So 10 minus 5 degrees in the denominator, those are my x. And so then I have to associate the temperature to the correct specific volume. So 10 degrees, the specific volume there is 106.32, subtracted by the specific volume at 5 degrees, 147.03. So make sure you understand the setup of this, right? It's very easy, very common if you don't put units to swap the specific volume and temperatures. It's also very common to swap the values, right? So you might have 10 minus 5 degrees here, but then you swap these values, in which case you'll have a sign error. So just check on that. And I'll show you another way that we can verify at least a sanity check at the very end to make sure that the solution we get at the end makes sense. All right, so at this point, now you're just solving for our one unknown. We have one equation, one unknown. So we subtract our numerator and our denominator terms here. So we get the simplified form. Same thing here, 6 minus 5 degrees Celsius is 1 degree. And then we try to isolate, right? So I move this 1 degree over, multiply it by 1 degree on both sides. So the units cancel out. That's why I like to keep my units consistent. And then I add 147.03 cubic meters per kilogram on both sides, and I can find my specific volume, right? So one sanity check that you can do is you take this value and you look at the range and make sure it's between the range. If the value you have here is lower than the smallest value or larger than the largest value, then linear interpolation is not done correctly. Because if you draw any line, the 2 points in your linear interpolation must bound your center point that you're interpolating for. In extrapolation, that's a different story because that's outside the bounds. But in interpolation, it will always be between it. If you find that your value is below or above the range that you expect, then most likely you have a sign error or if you swapped some of your values here, right? So we can see that it checks off. You can also see that this value is closer to 147 than it is to 106. And that makes sense as well because 6 degrees Celsius is closer to 5 degrees than it is to 10. All right, let's walk through another example using the same exact table. What if I wanted to find the saturation pressure at 34 degrees Celsius? I'll walk through this one a little quicker because the concept is exactly the same. So first we choose temperature as our x-axis, and I choose 30 and 35 degrees Celsius as my temperature range. Saturation pressure is right here. So these are the values that I'll be using in this equation. Then I set up my slope equation, right? So the unknown saturation pressure at 34 degrees Celsius minus, I choose the pressure at 30 degrees. If you want to choose the pressure at 35, you can. Just be consistent and swap out this for 35 degrees Celsius. But I chose 30 degrees Celsius as my reference point. So I have 4.2469 kilopascals. That's a unit of pressure, right? That's that value. Divided by 34 degrees Celsius minus 30 degrees Celsius. And then we equate that to the 2 points that were given, right? So the pressure, the saturation pressure at 35 degrees Celsius, 5.6291 kilopascals, minus the saturation pressure at 30 degrees, 4.2469 kilopascals, and then divide that by the temperature range, 35 minus 30 degrees Celsius. There, right? And we basically simplify and solve for our final pressure. And I'll let you walk through those steps, right? And again, we can do a sanity check. We have 5.3526, and that's in between these two. At least from that perspective, it makes sense. This value is closer to 35, the saturated pressure at 35 degrees Celsius, which makes sense because 34 degrees Celsius is closer to 35 than it is to 30 degrees Celsius. I've kept all my, like you may have heard of significant figures, right? There's a lot of significant figures here, just so that I don't have any rounding errors. But the very final stage, you may want to truncate depending on what you're doing. But that discussion of significant figures can be for another video. I'll do one more example, and I'll actually have you run through it before I walk through the steps. Okay, so for this one, I want you to pause the video, and I want you to see if you can find at 17 degrees Celsius what the internal energy of a saturated liquid is. So find the column with UF and find the two values it would use at 17 degrees Celsius. And then when you're done, come back and see if you match. You might not take the exact same steps as I do, but make sure when you come back that you've used the same 2 points and that you come up with the same final answer. All right, go for it. Press pause and try to solve for it. Okay, so hopefully you had a chance to try it out. So 17 degrees Celsius, hopefully you saw that that's between the 15 and 20 degrees Celsius range. Hopefully you saw that saturated liquid internal energy is this column here, and you use these values, right? So if you set up the way I did, I'd use the unknown and 15 degrees Celsius values, and then I'd use 20 and the 15 degrees Celsius values. So I'm going through this a little quicker because the previous 2 examples are exactly the same. Now, if you did it different, you can have the numerator and denominator swapped, you'll get the exact same answer. If you have the unknown 17 degrees Celsius values and 20 degrees Celsius values, you get the same exact answer as well, right? So here are my steps, and my final answer, I got 71.3532, which is in between the 2. So that's a good sanity check. Now you can go back earlier where I have that full equation of y3 equals the ratio of x the 0.1 and 0.2 values, right? That whole equation where you just plug into one final solution, you should get that same final answer as I do here. Now, one thing you might want to try, right? I use 15 and 20 degrees. Use something like 5 and 45 degrees. That is still keeping 17 degrees Celsius in between. See if you get a different answer. My guess is that you will for this example problem or the previous 2 example problems. And so that raises the question, why would you get a different answer? What is about linear interpolation, and what are the concerns about linear interpolation? And so that's what we're going to talk about on the next slide. So there's a few concerns about linear interpolation, or at least things that you need to be cautious of. Because if you're not, you're going to find a data point, use that data point in some engineering design or some analysis, assuming it to be a good reference, and you may not know how accurate or inaccurate you actually are. So some things to think about are, one, are the data points far apart? And I put this in quotes because it is very specific to the problem you're looking at, what far apart means. So in the previous slide, I mentioned, if you choose two temperatures to find your properties that are wider apart, it's still considered interpolation because you're still binding the unknown value. That doesn't mean that that's going to be accurate. So it depends on how accurate you actually want to be. So actually having some knowledge of what the problem you're looking at is extremely important. And the reason why when you have points that are further apart, that it becomes more difficult for interpolation to be accurate is unless the physics of the problem actually is linear, the wider apart you are, the less accurate you'll be. I wish I put a image here, but if you think of anything that's any line that is nonlinear, you can even think of a circle, and you pick 2 points on that circle, let's say, that are close together, and you draw a straight line. That's pretty close, right? Now, if you pick 2 points that are much further apart, like at the extremes, at the far ends of a circle, now you draw a straight line, you're drawing the diameter. That has nothing to do with the actual shape of that circle itself. So depending on the physics of it, what far apart means different things. And the last thing we need to be cautious of, sometimes we're given tables like I showed in the previous slides, thermodynamic tables, and we're going to assume that they're accurate. Sometimes we collect data ourselves. Then in those situations, we should have a better understanding of what error we might expect to see there. So the third question here is the data accurate enough? So what do I mean by that? So let's say that we have, again, looking at the same data sets, these 2 data points here, okay? And we're trying to use some linear interpolation to identify some unknown data point here. So we can draw a linear line here, assume that they're not too far apart, and assume that, you know, a linear relation assumption is a good one here. You can still have problems, right? Because it depends on how accurate this point actually is right there, and this point is actually right there. So you may have heard of things like error bars. So here, error bars represent what actual range accuracy do we know each of these points. So these bound the points. So a true linear interpolation would be a range of values that it could be. So any of the lines could represent any of these. So the point, an actual linear interpolation could be anywhere along here as well. So if we represent that as this specific point, that may not be accurate. And so, you know, I've walked through the steps of how to do linear interpolation, but in actual engineering and design practices, we need to be conscious of these 3 concerns, whether or not linear interpolation is accurate. In the future videos, we'll look at other types of interpolation, some linear, some 2D, some quadratic, and some higher level polynomial interpolations, right? Curve fitting, essentially. And how do we utilize and how do we determine which fit is the best? Can we use more than 2 points to help us make those fits? Those future videos will be coming soon. But understanding linear interpolation is important. Again, I will encourage you, if you're doing this in a class, to use the slope equivalency, right? Match the slopes, those 2 ratios, rather than just plug into the final equation, just so you have a strong understanding of what interpolation is doing. And after doing it a couple times, then feel free to use Excel or your computer and program in that final form so you can always just plug in and get your interpolation quickly.